Okay, now we get into second order linear differential equations. The second really main topic of this course. First topic was all the first order DEs. And they're important because they allow us to analyze the motion of objects which are influenced by some sort of a spring, something which is pulling at them, and there's often some sort of a friction, and of course the object has mass to it. And if you think about it, there are an awful lot of things in life that behave like that. Everything from a swinging arm to a car that's bouncing on its shocks, or a door that's going back and forth, or vibrations of a molecule. All sorts of things that vibrate back and forth, and a pendulum of a clock would be an obvious example. So there's all sorts of things that kind of swing back and forth in time. In fact, there's another whole collection of things which aren't mass but also have the same differential equation that satisfies them, namely electrical circuits. So there are an awful lot of things that can be modeled by this sort of situation. So let's start with the simplest example. Let's assume that we have a mass, and this mass is on a frictionless surface, and it's connected by a spring to a wall. So there's the wall. So Newton's second law says that the sum of the forces acting on an object is equal to the mass times the acceleration, and the acceleration is the second derivative of the position. So since the position of this object is going to be given by x, where this is the zero value and this positive is in this direction and negative in this direction, I'm going to take the second derivative of x. And typically, for whatever reason, when you use x as the function and t as the variable, then instead of writing x prime, I guess maybe that's one reason. Look at that, x prime. It could very easily lose the prime in the x there. And you could also write dx dt, but that takes up a little more space. And so instead of either of those, we use, I think it's Isaac Newton who actually came up with this idea, as a dot for the derivative. And so the second derivative is going to be x double dot. So that's just another notation for the second derivative of x with respect to t, and times the mass is the sum of the forces. And again, we're assuming that the only force acting on this thing is due to the spring. And there's another scientist that lived, I think, about the same time as Newton. His name was Hooke. And he discovered, among other things, that the force that's exerted on a spring, or that a spring exerts, is proportional to the displacement. If you have something which is like this, and you put, like at the grocery store, and you put 1 pound of melon on it, it's going to go down this far. If you put two melons on it, it's going to go down exactly twice as far. So the displacement is proportional to the force. And Newton's third law says that there's always a equal and opposite reaction. So if this spring is stretched down here due to a 2 pound force, well, then that means that the spring is exerting a force upwards with 2 pounds as well. Okay, so the point is, this spring is going to be exerting a force on this mass, and that force is proportional to the displacement. So we need a proportionality constant, and that's going to be k. It's just basically the stiffness of the spring. The larger k is, the larger the force is going to be for any particular displacement. So let's think about it. If this thing is over here, then the force is going to be moving in this direction, which is negative. And on the other hand, if the displacement is negative, this is the natural place. This is where it just wants to relax. If you push it this direction, then the force is going to be positive. It's going to be pushing it away. So if we want k to be positive, and I always like my constants to be positive so I don't have to remember which ones are positive and which are negative, then it looks like we're going to need a negative k x. So let's just check it again. When x is positive, and then x times this is going to be negative, so the force is going to be this way. If x itself is negative, then negative times negative is going to be positive, so it's going to be this way. So there's our differential equation right there, and we can bring this over and get mx double prime plus kx is equal to 0. So there is a second order linear differential equation. Remember, it's linear because the only things that we're doing with the function and the derivative are just letting them sit there. We're not taking the square root. We're not taking 1 over them. We're not squaring them or anything else. We can do whatever we want in front of them, but these things themselves we don't play with. So it's a second order linear differential equation. So how do we solve it? Let's throw in some numbers now and get a particular one to solve. Let's say that k is equal to 9, and let's say that m is equal to 1. So let's take that as an example. And so we're going to get x double prime plus 9x is equal to 0. And so that's what we need to find the solution to. And again, I'm going to go backwards again, I guess, and just say that this implies that x double prime is equal to negative 9 times the function. So I'm going to challenge you now. Can you think of the solution of this just by, it's called by inspection, just by thinking about it without doing anything fancy? Can you just guess the solution or a solution to this? Basically, what do we want? We want some function so that when you take the second derivative, you get that function back with a negative 9 in front. So let's think about, let's just play with this. Let's just play with it a little bit. If the function were e to the 3x, or 3t rather, then when we take the derivative, x prime, that would be 3e to the 3t. And when we take the second derivative, it would be, multiply this by another 3, it's going to be 9e to the 3t. So we're kind of on the right track with that, but notice that we want a negative 9 there rather than a positive 9. So you could try putting a negative here, but this is going to be a negative, and that's going to be back to a positive again. So this is 9 times that rather than negative 9 times that. So that doesn't work. So by the time we take the second derivative, we want just one negative rather than two negatives. So if as I say, if this were a negative there, we'd end up with two negatives out front, which makes it a positive. So that's no good. So let's see, how would we get just one negative? Oh, now maybe you're thinking, what about the sine of t? If you take the derivative, you get the cosine of t, and when you take the derivative of that, you get back negative sine of t. There's our one negative. That's what we want. The problem is we don't have the 9 there. So how can we get the 9 there now? I'm hoping that if you're really ambitious, you stop the video from time to time and see if you can do it on your own. It's just like playing Wordle or Sudoku or something. Just think of it as a challenge. What if we put a 3 here? And then this is going to be 3 times cosine of 3t. And then you take the derivative again, it's going to be negative 9 times the sine of 3t. Aha! There's what we're after. There's a function that when you take the second derivative, you get negative 9 times the function. That's what we're after. Can you think of another one? Hopefully you realize that this thing has a partner. They're never too far away from each other. If we call this one x1, let's call this one x2. x2 is going to be cosine of 3t. Then if you take the first derivative, now you get the negative already, negative 3 sine of 3t. And then when you take the second derivative, you bring another 3 out, you're going to get negative 9 cosine of 3t again. See that? So those work. And not only would those work, but any constant times those would work. If you'd started off here with a 5, then the 5 would just be carried through, and you'd end up with a negative 45 right there. And it's still the case that this is 9 times this. See that? So we've got a bunch of solutions. In fact, it turns out that if you were to add those together, that would also be a fine solution. So let me just write it like that. Let me write it as a times sine of 3t plus b times cosine of 3t. That's going to be a solution because just check it out. Everything works. Everything. If you take the second derivative, you're going to end up with -9 times the one that you started with. So maybe you're starting to notice now that this kind of connects to what we were doing in the last chapter. Something's kind of linear here in the sense that that this is a solution and this is a solution, and then we can, or I should say, this is a solution and this is a solution, and so we can get a whole lot more solutions just by adding them together and by multiplying them by constants. Does that remind you of a vector space? A vector space where you have particular vectors and you can take linear combinations of them by multiplying them by constants and adding them together. And in fact, we're going to be digging into the theory of this more in the next section or so. And so I'll just kind of tease you with it here, but that's underlying this, just like it underlies much of mathematics, as I mentioned to you back when we were discussing vector spaces. So anyway, this is in fact the general solution. It has two linearly independent vectors, and so these two right here make up the basis for the solution set for this differential equation. And every solution to this thing right here is in this form. Okay, so everything is of this form. This and this form a basis. You take linear combinations of them and you're going to get everything. So there's your general solution to this differential equation right there. So once you have that general solution, then given the initial conditions, you can find what A and B are. So the one I have in the book, let me see if I can find it here a second. I said suppose that your initial position is 5 and your initial velocity is 6. Okay, I think that's what I have. Okay, so in other words, here's what we've done. We've pulled this mass out. It's now starting at 0.5, and then we give it a shove. We give it a shove in this direction so that the initial velocity is 6. So what's it going to do? It's going to keep going this way for a moment, but then it's going to back up and go this way, and then it's going to go this way, and it's just going to keep oscillating. There's no friction here, so it's just going to keep oscillating back and forth. So let's see once if we can get the equation of motion for this system. So I need to find what A and B are. So let's do it. First of all, here's what I know. I know that x of 0 is going to be equal to 5, and if I stick a 0 in here, sine of 0 is 0, the cosine of 0 is 1, so it's going to be is equal to b. Well, that was easy enough. Is equal to b, so b is equal to 5. Let me just, for sake of time, put that right there. And now, what about the derivative? Now we're going to have to take the derivative first, so we get x prime, or x dot. I'll say the word prime probably, even though I put a dot there. If you take the derivative, you're going to get 3a cosine of 3t, and then it's going to be minus 15 sine of 3t. Everyone agreed? And so that's the derivative, and we know that when I stick in a 0 there, what are we going to get? Stick in a 0, this is going to be 0, this is going to be 1, so you're just going to get 3a, and that is equal to 6, which means that a is equal to 2. So again, just for sake of space, I'm going to go ahead and just put that in there right there. Okay? So, there's our solution. This thing right here, if you went to Decimus and graphed it, you would see what x of t does. Here's your t-axis, and I guess your vertical axis would be x, and so the height would indicate how far this thing is moving in both directions. Now, this isn't a bad solution. As I say, Decimus will handle that for you, but I want to show you a really clever trick that we're going to be using throughout this book, more than just right now, in order to write this in a better form. Here's what we're going to do. Let me show you. Here's what we do. It's very clever. We take these two numbers and we square them and add them together. So 2 squared plus 5 squared is equal to 29. Agreed? And so we are going to divide, well, here's what we're going to do. We're going to both multiply and divide by the square root of 29. And you'll see why in a minute. So I'm first multiplying out front, and then I'm going to have 2 over the square root of 29 times the sine of 3t plus 5 over the square root of 29 times the cosine of 3t. Okay? Now, why did I do that? I did that because I manufactured these numbers right there so that when I square this one and square this one and add them together, I'm going to get 1. Do you agree? If I square this one, I'm going to get 4 over 29. If I square this one, I'm going to get 25 over 29. 4 plus 5 is 29, so I have 29 over 29. So in other words, those are numbers right there which are on the unit circle. Okay? I have 2 over square root of 29, and then 5 over square root of 29 right there is going to be the point. 2 over square root of 29, comma 5 over square root of 29. There they are on the unit circle. Okay, 2 over and 5 up. Okay, so there it is right there. Now, why is that anything I want? Well, because I happen to know my trig. And I know that if you're at a point like that on the unit circle, then there's some angle right here, let me call it gamma, such that this thing right here is the cosine of gamma, and this thing right here is the sine of gamma, right? The cosine is this, and the sine is this. So in other words, there is a gamma such that this thing right here, let me write it like this, is equal to square root of 29 times, and now I'm going to put, excuse me, this one first, sine of 3t times cosine of gamma plus cosine of 3t times the sine of gamma. Okay? And why do I want to do that? Man, it looks like I'm just making things a whole lot worse. But now comes the clever thing. When I teach calculus, I remind my students, or pre-calculus for that matter, that there's a really valuable formula for the sine of the sum of two numbers. The sine of a plus b, you do it like this. You go sine, cosine, cosine, sine, cosine, cosine, sine, sine. That gives you both this one and the cosine of the sum of two numbers. But you take the first one, sine, cosine, cosine, sine, and then you alternate putting AB, and then you put a plus right there. Okay? So notice that's exactly what I have here. I have the sine of this, cosine of this, cosine of this, sine of this. So this thing right here, there's your A and your B right there, A and your B. So this thing right here is just the square root of 29 times the sine of 3t plus gamma. And that is a much nicer form than this because it does two things. First of all, it tells you that the general shape of this thing is just going to be a sine curve, okay? It's going to be a sine curve where if this were a t right there, the period would be 2 pi. It would start up and down every 2 pi. With the 3 in front, it's going to be 2 pi over 3. So the period is going to be 2 pi over 3. That's when it starts over again. The gamma is just going to shift it, but that's not a big deal. That's when you're talking about the movement of this thing, you generally want just kind of the general movement. You don't care exactly where it is at a particular point in time. You want to know just kind of what the general movement is. So now we know that this thing is going to be back and forth. It's going to be a full oscillation every 2 pi over 3 units. And just as important, we know that the amplitude is square root of 29. So in other words, you took this thing and you started it at 5, and then you gave it a shove in this direction. Well, 5 square root of 29 is bigger than 5, right? Because 5 squared is 25. Let me make sure you're still with me here. Okay, very good. Okay, 5 squared is 25, so this is bigger than that. So the fact that you gave it a positive shove meant it went all the way to the square root of 29, just a little bit farther, somewhere around 5.5 maybe. And then it got pulled back, and now it's going to come back, and it's going to go out to the square root of 29 again, and down here to the negative square root of 29. This just keeps bouncing back and forth between those two values. There's no friction, so it's just going to keep bouncing back and forth between those two values, and it's going to do that. It's going to make one full. Here it's going to do this whole thing. Whoa, there's a period right there. So starting here, back there again, that's going to be every 2 pi over 3. So that's pretty good motion. That's pretty good understanding of that thing. Okay, so that's how that all works. Okay, now let's throw in friction. So we'll erase all this stuff. And now we're going to assume that there is friction here as well. So this thing could be rubbing on the surface, or it could be going through water or something like that. The way you designate friction on a diagram like this is you put a little, it's called a dash pot. It's kind of like you put a little plunger there. And then you think of this thing as being fixed with oil in it, and this plunger is going through the oil. Get the idea? So it's just, it's pushing through that oil, that viscous oil, and we're going to let C stand for the viscosity. Okay? Well, how's that going to affect our differential equation? First of all, K is still positive here. Okay? Mass times acceleration is equal to the sum of the forces. But now we not only have the force due to the spring, we have the force due to the friction. And as before, the frictional force is going to be proportional. Well, I say as before. As is typically the case when you have something moving fairly slowly, the force due to friction is proportional to the speed. So here's your proportionality constant to the speed. There's the speed right there, x prime. Okay? So now the only thing we have to worry about is this a positive or a negative? Let's figure it out. If x prime is positive means we're moving to the right. Okay? If the derivative is positive, that means the x is increasing. So if the derivative, the velocity is positive, that means that the function is increasing. It's going like this. And let's think about it. If it's increasing, it's pushing through the fluid, so the fluid is going to be pushing back on it. So if it's moving positive, then the force is going to be negative. On the other hand, if this thing is moving to the left, if the velocity is negative, then the force is actually kind of trying to push it positive again, right? It's resisting the motion, so it's pushing it positive. It's in the positive direction. So it looks like we want a negative here again, so that when this thing is positive, the force is negative, and when the velocity is negative, the force is positive. So there we go. So let's see what this one looks like. So it's going to be m x double prime plus cx prime plus kx is equal to 0. So there's another second order linear differential equation. It's not one that we can do just by inspection the way we did the other one. This one's more complicated, but it is a second order linear DE. And so now we need to learn how to solve this sort of thing. So we're going to take kind of a parenthesis now, and we're going to kind of step away from the thinking about the masses for just a little bit, and we're just going to concentrate on how do we go ahead and solve anything of this form for any values of m, c, and k. And then once we learn how to solve anything like this, then we're going to start applying it back to the masses again. Okay, are you with me? So I'm just following the book. And so the first one that we're going to do is going to be this one right here. So notice that this one right here is not even one that physically makes sense, because I've got a negative c there rather than a positive. So this would not apply to a spring system, but it is a second order DE, and it's the type of thing that comes up in solving DEs quite a bit. So we want to learn how to do anything like this. So let's learn how to do this one. And I'm going to make this thing just one. Okay? So there we have it. So how do we go about solving that? So here's what we do. We first of all, we let L be a linear transformation. Does that word ring a bell? L is a linear transformation, and L is a linear transformation that does this. It takes the function x and it does this to it. It first takes the second derivative of x. Well, it just does this. It takes the second derivative of x, and then it subtracts 5 times the first derivative of x, and then it adds 6x. That's what it does to x. So if you want to just express what L is, you'd say L is this. And again, I'm following the book. If you were just to express it, you'd say L does this. D stands for the derivative. It takes the second derivative of something, then it subtracts 5 times the derivative of that thing, and then it just adds 6 times that thing. So you could think of this as a function. If you stick x in there, what does L do to it? It takes the second derivative of it, then it subtracts 5 times the first derivative of it, and then it adds 6 times whatever that function is. That's what it does. Okay? So that's a linear transformation. We played with this sort of thing in the last section and showed why this thing was linear. We did it for just a D, but the same thing applies here. You can show that it's linear, let's just take a moment. So let's take x1 plus x2. So this is one function, that's another function. So what does this say to do? It says to first take x1 plus x2 second derivative of it, then subtract x1 plus x2 the derivative, and then plus 6 times x1 plus x2. And this thing you can break up and you can write it as x1 double prime minus 5x1 prime plus 6x1, and then you can do the same thing with x2. And so notice that that's just L of x1 plus L of x2. See that? So it's linear. Well, I did the first thing. Now you have to do the same thing by multiplying by a constant. But the point is, all the stuff we're doing now just relies on the fact that these things are linear. This is a linear transformation right here. Okay? So I guess that was good to go through that. Okay? So anyway, let's see how this one can be kind of broken up a little bit. Notice that this thing factors. I can write this as d minus 3 times d minus 2. Agreed? And so what we have here is we have, when will L of x be equal to 0? So we want to know, right? This thing here is equal to 0. So we want to know, when will this thing be equal to 0 when we apply it to x? So if I apply this thing to x, when will this thing be 0? It'll either be when d minus 3 applied to x will be 0, or it will be when d minus 2 applied to x will be 0. And this just means that the derivative of x is equal to 3x. I'm going to bring the 3 over, and this just means that the derivative of x is equal to 2x. Well, these are things, here, now we're back to our old friends again. This is just a first order linear differential equation. one that hopefully you know how to do, right? We could do this one by separation. This is what? Dx dt is equal to 3x. So you bring the x down, and you bring the dt over here, and you integrate both sides, and you're going to get, by the time you're done, you're going to get x is equal to e to the 3t with a constant out front. And similarly here, you're going to get e to the 2t. So by the time you're done, you're going to get two answers, e to the 3t with any constant out front, and here you're going to get e to the 2t with any constant out front. And these two things are both solutions. They are linearly independent. What does it mean to be linearly independent? You only have two of them, so I can't get this one through a combination of these. Nope, I can't, because they would have to be the same function. This is not a multiple of this one. So they're linearly independent. I have two of them, and we'll learn in the next section that that's going to give us the complete solution. So this thing right there is our general solution, like that. Okay, so there's the general solution of this. Then if you want to, you can say, okay, I think I do this in the book. I won't go through it all here just for sake of time, but I say let's just say that x of 0 is equal to 8 and x prime of 0 is equal to 10. So let's just get started. So x of 0 is equal to 8, and so that's going to be equal to, if I stick in a 0 here, I'm going to get a plus b. Agreed? So 8 is equal to a plus b. Now if I take the derivative, what do we get? We're going to get x prime is equal to 3a e to the 3t plus 2b e to the 3t. And that's the derivative. If I stick in a 0 here, x prime of 0, I'm going to get 3a plus 2b, and we're told that that's equal to 10. So now I've got two equations, two unknowns, and so now I need to solve them. So heck, I guess we might as well do it. We have a plus b is equal to 8. We have 3a plus 2b is equal to 10. So what's the way to solve that thing? Let's see, if I multiply this equation by a -2, I'm going to get a -2 here, a -2 here, and a -16 here. Then if I add them, oh, this is a -2, then I'm going to end up with a, these cancel out, this is a process of elimination, is equal to -6. And once you have that a is equal to -6, then you're going to get b is equal to -10, hopefully. Let's see if I get the same thing as I did in my notes. Oh, I got -6 and 14. Did I do that right? Let's do it again. I'm sorry. We have that a plus b is equal to 8. A plus b is equal to 8, and we're told now that a is equal to -6. So we have -6 here, so bring it over, and b is equal to 14. Okay? So that gives us our particular solution, given the fact that what's happened. What have we done now? We've pulled it off. What have we done, or how did we start? We pulled it off to a point 8 units up, and we gave it a push this way, and a positive push, and now it's going to go back and forth. Well, no, is it going to go back and forth? I'm going to let you decide. You determine whether it goes back and forth. Here's the solution. You go ahead and put that into Decimus and discover what happens. Okay? Well, actually, no. This doesn't even make sense physically. This isn't friction. Anyway, for this particular DE, go ahead and find the solution of this thing and see once on Decimus and just see what happens with it. Okay? So there's that. Okay, let me show you another way to get this solution as well. These are both different ways that are kind of important for things we're going to do later on. Another way to do it is just to say, hey, whenever we have differential equations like this, often we get solutions of the form x of t is equal to, and again I want to follow the same notation as I have in the book. And so we just say let x of t be equal to e to the lambda t. We just say let x of t be equal to e to the lambda t. And let's just see once if there's any solution of this form in this thing here at all. So let's check it out. So what happens if we just stick this in here? We're going to get the second derivative of this. Can you do it in your head? If you take the second derivative of this, it's going to be lambda squared e to the lambda t. Then you're going to get minus 5. If I take the first derivative of this, I'm going to get lambda e to the lambda t. And then finally 6 e to the lambda t. So if there's anything of this form that makes it true, let's see once what happens. I set this equal to 0. Notice that I can factor an e to the lambda t out, and I'm left with lambda squared minus 5 lambda plus 6 is equal to 0. And that's just a quadratic. This is going to be 0 whenever this thing is 0, and that thing can be factored into lambda minus 2 times lambda minus 3 is equal to 0. And so lambda, obviously, this thing will never be 0, is either equal to 2 or 3. So that tells me that there are two solutions of this thing, e to the 2t and e to the 3t. And again, notice that they are linearly independent. There's no way I can get this one by just taking a constant times this one. So they're linearly independent. And so I know we'll learn in the next section that the dimension of this solution space is 2. And so since I've got two linearly independent vectors, I've got all that I need. And so if I just take all possible combinations of those, I'm going to get the general solution. So there's your general solution right there. So that's another way of doing it. Okay? Very good. So now in the book there are several other problems, exercises for you. Exercise 3, 4, and 5. So I'll let you do those. Now let's go to example 6, which is something a little bit different. Okay, I'm just going to get rid of this for now. And we're going to look at this one. So it's going to be x double prime. This is example 616. And here it is, x double prime minus 6x prime plus 9x is equal to 0. Okay, well, let's try it the same way we did the other one. By the way, I guess I forgot to mention, in that other one, basically all you have to do is you just take this thing becomes lambda squared, and this becomes minus 6 lambda. Lambda just is your derivative, that's the second derivative, plus 9 is equal to 0. And this is called the characteristic equation. Okay, so you can get it just easily. The previous one, I guess I already got for you, but it was what? Lambda squared minus 5 lambda plus 6. And so that thing factored into lambda minus 2 and lambda minus 3. Okay, now we have this one. So what do we do with it? So we're going to get, if you factor that, you get lambda minus 3 times lambda minus 3 is equal to 0. And let's see, am I running out? I might have to grab myself another marker here. And so we get e to the 3t right there, plus beta e to the 3t there. And the question is that the general solution? And hopefully you realize, no, it's not. There's no reason. These things are not linearly independent. This thing is in fact equal to this thing, right? So they're not linearly independent. In particular, there's no reason to say alpha of them plus beta of them. It's just alpha plus beta. You don't need that there twice. Okay, it's just like having the same picture on your computer twice. Okay, it says no, either replace the one or get rid of the other one. Okay, so we only get one of them that way. Okay, we only get one of them that way, and so we got to figure out a way to get the other one. We know that there's two linearly independent solutions to a second order linear DE. So we have to find a way to get the other one. So here's what we do. We go back to what we did before. We say L is equal to D squared minus 6D plus 9. And L of X is going to be equal to 0. So that's true. Now you can write this as D minus 3 times D minus 3 of X is equal to 0. That thing factors. Okay? And now you can write that. This place I always need to watch myself. So this thing right here is going to be, we're going to call that W. And so now we can write D minus 3 W is equal to 0. Okay? So how's that going to help us? Well, W is the solution to this. So D minus 3 X is equal to W. W is the solution to that. So let's go ahead and solve it. Oh no, let's solve this one first. This is the one we can solve first. So what do we have here? We're going to get W prime is equal to 3W. Agreed? W prime is equal to 3W. Well, I got to make sure you're still with me. Okay, very good. Computer's working well. So I know already that W is of the form just some constant alpha e to the 3t. Okay? In order to satisfy this, W's got to look like that. Now I can go to this one and say, let me show you what it is. It's first of all the derivative of x, so it's going to be x prime minus 3x is equal to W. And we already know what W is now. W is equal to this. Okay? Can we solve this? Yes, we can. This, notice, is a first order linear DE. So we learned how to do that back several sections ago by using the formula for a first order linear. And it turns out, we won't go through all the process here, but remember you have that integrating factor, e to the p integral of px and so on, and this is e to the negative integral and so on, q of x. I can't remember what we all used. But anyway, the solution is this. X of t is equal to alpha t e to the 3t. Okay? So there's the solution to this thing, plus some constant. And so we have this. We also have the original one. Oh, no, I'm sorry. No, I'm sorry. Let me just check my notes here very fast. We get all this. We get all this. Okay, we get all that right there. So by the time you're done solving this thing, you end up with this. So it turns out now we have our full solution, because notice we've got two solutions right here, and they are linearly independent. I can't multiply this one by a constant to get this. I can't multiply this just by a constant to get this. This has a t in front of it. This one doesn't. So they are linearly independent, and so there's your solution right there. Okay, so that's going to be very important as we go on. Okay, very good. Okay, so that takes care of example 616. Now, there's only one more left to do, which is something a little bit different from everything else. Suppose we have this one, x double prime plus 2x prime plus 10 x. X double prime plus 2x prime plus 10x. Notice that this thing now is back to this sort of a situation. This is positive, that's positive. So we've got ourselves a something that models a physical system where the mass is 1, the frictional constant is 2, and the spring constant is 10 in this case. Okay? Okay? So let's use the same technique we had before. We'll start off with our lambda squared plus 2 lambda plus 10 is equal to 0. And we will solve it for lambda. So notice I can't see how to factor this thing, so I'm going to use the quadratic formula. Lambda is equal to what? Minus 2 plus or minus the square root of 2 squared, which is 4, minus 4 times 1 times 10, minus 40, all over 2, which is equal to negative 2 over 2 is a negative 1. And then let me do some of this in my head here. This is going to be a negative 36. The square root of 36 is 6. 6 over 2 is going to be 3. So it's going to be plus or minus 3, but it's negative, and so when you're going to have that 36 times a negative 1, and the negative 1 gives you an I right there. So there is those are the roots to this characteristic equation. So that means that my general solution is going to look like this. Alpha, I can't remember, did I use alpha? I did. Alpha times e to the negative 1 plus 3i t plus beta e to the negative 1 minus 3i t. What do we do with that? What do we do with that? We've got complex numbers in there. How does that affect things? Well, here is where I give you two different full explanations in the book of how to get the answer, and this is going to be where I'm just going to let you read through the material in the book rather than me going through it all. Instead, I'm just going to give you the answer here. Here's the solution. Instead of writing it like this, it turns out that you can instead write it like this. Be different constants, I'll call those like that, and so it's going to be like this. X of t is going to be alpha e to the negative t times the sine of 3t plus beta e to the negative t times the cosine of 3t. Okay? It turns out that this number here just becomes the number that you put right there, and then this number there goes for your sine and cosine. In general, if this were an A, and this were a B, and this again were an A, and this were a B, let's just make that a positive A there. Positive A, and these are always, one of them is positive, one is the negative. Then this is going to be e to the AT, and this is going to be e to the AT, and then here's your B. It's going to be B like that, and it's going to be B like that. So there's your solution. You instead of playing with it like this, you can write it like this. And the reason is, I want the details are in the book, but the reason is that and I go through the details here, but e to the IT turns out can be written as cosine of t plus I sine of t. Okay, that's called Euler's formula. Euler is spelled like this, Euler's formula. And because of that, you can take these two things and you can add them together and end up with one, and you can subtract them from each other and get the other one. And we learned back in the linear algebra section that if you have two linearly independent vectors, u and v, then if you add them together and if you subtract them, you're going to end up with two linearly independent vectors. And you can also divide them by constants, or multiply them by constants, and you'll get two linearly independent vectors. So that's what we're doing here. We start off with these, and by adding and subtracting certain ways, you can get it to look like this. So that's the idea. So that's the solution. And the important thing to notice about this is that with these sines and cosines, now the solution is going to be very different from where we just had exponents. When we just had exponents, the general solution, either it started here and it just went down it basically went down to zero. The friction just brought it down to zero, or depending on your initial conditions, maybe it overshot. It finally died on me here. Maybe it overshot. Okay, if it overshot, maybe it started here and it went down and then it came up and it looked something like that. But if you just have things of this form, e to the negative t and e to the negative 3t, and maybe t times that, depending on whether you have a double root like we did before, you're going to get things that look like this. They may overshoot, they may not, but at the very most, they're going to do this. Over here, it's going to do what? Maybe it starts here, maybe it overshoots the equilibrium, 0, and then it comes back. Or maybe it goes up here and then just slowly dies like that. Do you see that it's going to depend on the relative sizes of these things? Just think about it physically. If you have a lot of friction, so you've got maybe a very weak spring and a very small mass. So you've got a light mass and a weak spring, and you've got a lot of friction. This thing, even if you give it a shove, is just going to, the friction is just going to slow it down. It's going to go like that. It's just going to go towards equilibrium. The spring will just very slowly pull it to equilibrium. So it'll look, maybe it'll start like that. Maybe you pushed it in this direction, but it's going to slowly do this. On the other hand, if you have a stronger spring or a heavier mass, then depending on the sizes of these things, then what might it do? Maybe it'll, especially if you push it in this direction. If you push it in this direction, it'll overshoot. But now that it overshoots, it'll just slowly coming back. So that would be something like this. It overshoots, goes negative. Here's the negative territory, and then slowly comes back. But if you have very small friction and you've got a thick, heavy spring and maybe a heavy mass as well, we're going to be digging into all this stuff later on, but I want you to be thinking about it even now. Then you think about it, you've got a big, heavy spring, you've got very light amount of friction. That friction is eventually going to slow it down, but it's going to take a while. It's going to just keep oscillating. So it's just going to, in this case, it's going to oscillate back and forth. And those oscillations are going to become smaller and smaller, and that's the kind of situation you have here. See this right here? You have a negative, and you had a -1 there. So what happens? Can you if you were to do that same little trick with finding writing it like this, you could write it as beta. Let me write it as gamma times e to the negative t times the sine of bt plus some angle there. What's this going to look like? Do you remember this from pre-calc? This is going to be a sine curve which oscillates, but this is going to be your amplitude. So your amplitude is e to the negative t, and that's going to look like this. It's going to keep getting smaller and smaller. If you take the negative of it, it's going to look like this. And so this sine graph oscillates within this envelope, and so it just gets smaller and smaller as you go. So that's what we're going to be spending time on in the next couple sections, is really analyzing this stuff and getting a good sense of it. So it's all fun stuff. And the point is, when you do these problems, and I'm trying to force you to do it, but work with me as you do these problems. Think through, what would you expect the motion to be just by looking at these relative sizes of the spring constant and the friction and the mass, and given that, what would you expect the motion to be? Okay, a lot of good stuff in this section, so we'll go on from here.